Or you just, oh, never mind, you are.
No, thanks for telling me. So, and then as a something for the control type problems on the final exam, like there's something wrong, fix it. Those will all be second order. Okay. The material as presented for just to make sure that there's no polls on the right hand side. It's not, there's more to it for third degree and above. For second degree, it works just fine. But when I was trying to create an example, I realized that the way that was presented wasn't right. But what is right is that if something's missing or negative, you have to have it, and then you have to make it positive. You just have to you might have to make it greater than 1. And so on the grading of the midterm, it'll, did you identify the problems, and did you come up with a G of S to actually solve the problem? Now, if you don't get the constants right, that's okay. All right. And in fact, this stability analysis, it's a whole area of research, and it's EE 132, where you'll learn to do higher order than second order. So really, even though for some filters and things we've done fourth order, really this 110 is about first and second order things. All right, just to help focus. Also, the not to ruin everybody's mood, but the final exam is on the 10th of December. That's what's in the green sheet and on the university website. Now, if you have more than 2 exams within a 24-hour period, it doesn't have to be on the same day. It's within a 24-hour period. It's getting to the time where you have to request a makeup. All right, I've already got a makeup person for the makeup day, which I believe is 16 December. And usually I just start that at 9 o'clock in the morning. So if you're running into that kind of thing, you don't have to, and 110 is a class that you can move. Just let me know so that I know who to expect and who not to expect. All right. So a lot of what the system identification is the opposite of what we've been doing. Is I give you a transfer function and you plot it. Here you get a transfer function and you have to tell me the Bode plot, and you have to come up with the transfer function. Now the thing is the answer you get does depend on what you assume the original thing is. And a computer can give you an algorithm, can give you an answer, but it might be garbage. But still, you have real numbers but the garbage might be, applying the wrong filter. And, there's this old joke about that before artificial intelligence, there was something called expert systems. And they tried to program in everything a doctor would do and ask, and then make a diagnosis. Well, and they made a computer program. Well, somebody went and described, their rusting Chevy Nova, right? Described the symptoms to this expert system by just typing in the answers. And of course, the artificial intelligence doctor gave a diagnosis. It was a garbage diagnosis because, of course, the tool was being used, in a funny way. All right. So if you assume a low pass filter, but it's really a high pass filter, you'll get numbers, but it'll be garbage. And so when you look at the Bode plot, yeah, you've got to recognize right the shapes, right? And so that low pass, right, it comes down with frequency. High pass, it comes up and levels off. Band, you know, some shape like this. And none of the above filter. Notch, kind of has that shape, right? Or even, you know, you could draw that symbol, right? And band pass, you know, you could kind of draw it asymptotically, right? Then, you know, once you identify, oh, this is a low pass, well, looking at the slope here will tell you the order, right? That it's 20 dB for first order, for minus 40 dB second, and so on. Same with the high pass, right? And, you know, this is, oops. You know, it's easy to see that that's omega naught right there. That's how we did it for asymptotic Bode plots. So in a way, what you do is you get a, and we'll go into this, you take a Bode plot that's fully calculated, and then you draw an asymptotic Bode plot on top of it, right? Now for these kind of filters where you have a damping ratio, right? And if it's greater than one, it's overdamped, two real poles. If it's equal to one, it's repeated. And if it's less than one, it's underdamped. It's one pair of complex poles, right? And what that can do is cause like a peaking, right? Or if it's like this, where there's a break frequency here and a break frequency here, right? Which we did on midterm one, where we did a high or a low pass filter and we had two distinct real poles. Maybe they got closer, maybe they got farther apart, but we never got into a damping ratio of less than one. All right, this is now where we get into that. All right, but and then just this is like a philosophical caveat, right? Is that, you know, this is a notch filter. That's my eye looking, right? I'm looking between these frequencies. And so it's behaving like a notch filter. But what if, you know, out here, it does something else, right? The transfer function tells you everything it can be, but the picture, you'd have to look at infinite frequencies to see what's going on, right? So it is somewhat dependent on what you look at. All right. Any questions so far? Okay. So here is a first order low pass filter, right? And if it is first order, right, which, you know, I can go in here and see and calculate, oh, the slope is minus 20 dB per decade, right? So if it is first order, it has to be real, because in order to have complex poles, you have to have a system, a second order system, all right? Now, how do I find this gain DC? Well, just like in the asymptotic Bode plot, right? Set omega a lot less than omega naught, right? And then this will cancel out, then the omega naughts will cancel out, and I'm left with my GDC. So right here, right at 1 hertz, I'm reading 0 dB, right? Which then, in order to make sure to convert things back to linear, not in a dB scale, right? So 10, 0 to the 20 is 1. So we identified it's a first order, and we have the gain. Now, where's omega naught? Well, there's actually two ways to do this. One, omega naught occurs at minus 45 degrees for a first order system. So I come out at minus 45, all right, and then I drop it down and like, oh, it's at 1 kilohertz. Okay, that's one way to do it. But what I've found in actually measuring systems that this phase is actually a normalized delay to frequency, right? So a 1 hertz sine wave that isn't delayed at all has 0 phase, right? But here, the 1 kilohertz sine wave delayed by 45, by minus 45, that's an actual time difference between the peaks, all right? That measurement of the peak, the change in peak, is very hard to calibrate, I've found, right? And so what I'm about to say is this minus 3DD point and the minus 45 point sometimes don't match very well. Okay. What can be good about the phase is, it starts off at 0 and goes down to minus 90. That means the transfer function is positive. If it started off at 90 and went down to 0, right, then I'm like, oh, okay, that's a negative transfer function. All right. Anyway, we can find omega naught in another way, and that's by drawing the asymptotic Bode plot. So if I draw out the DC gain here, and then now I'm doing this by hand, so it's going to be a little stinky. Okay. Right where they intersect is where you'll get omega naught. Okay. Now, yeah, I did this by hand rather than a nice, like with a ruler. And so you can see there's a little bit of difference between omega naught, what I did here and what I put here. And that these problems are all human graded, and assuming that you are not using LT Spice to extract it, but doing it just like I'm doing it, maybe a little neater, right? And so that there's there's a tolerable error, right? So the fact that if maybe you got 9 or 8 or 11 or 12 kilohertz, okay, but 100 or 10,000, well, that wouldn't be okay. All right. And so you measure the frequency, right? But then you have to convert it to radians. So you multiply it by 2 pi. And that 1 is the gain at DC. And there you go. You've identified your first system from a Bode plot. So what kind of system do we have here? Pretending not to read the title. Anybody in chat? High pass.
Oh, high pass.
Okay, yeah. High pass. Now, by I wouldn't necessarily anybody be able to tell me that slope is 20 dB, right? I'd have to okay, that's around 42. Okay, that's around, so yeah, all right, that's 20, right? Now with the phase, it's a little bit easier because I can see that it's the way I plotted it, it's going from 90 down to 0, right? But I'm sorry, I want to make that minus 100. The thing is that this is a root on the right-hand side. And this ends up giving you another minus 90 degrees of phase. And so when you were plot this out, you'd have you would have a plot that you might not really recognize. Okay. This can happen, right? But you're not, so when you're learning what I'm telling you, remember about, like if you look at the slope and say, well, if the order is n, a second, third, fourth, fifth, that slope should be n times 20 dB per decade, right? And that's like a pretty good rule to remember. And then when you talk about the phase, 0 to minus 90, right, times n, that's kind of pretty good to know. But when you start having poles on the right-hand side, right, roots on the right-hand side, it can play with this phase thing, and that you see that later. But in 110, you don't have to worry about it. All right. But I know sometimes people have questions. That's why I mentioned it. Okay. So oh Eric, I want to answer your question a little bit later in the second order, because omega naught isn't always the cutoff frequency. All right. Um, to Javier's question, are we getting the cutoff through the phase? Yes, you can do it through phase, and you can also do it through the magnitude way. And then I'm not quite sure, Nick, when your question came in about calculating the cutoff frequency, it's really omega naught is the correct term. For first order, they are the same thing. Or first order repeated poles, they're the same thing. Okay. Yeah, you only need the magnitude. And all you really need is a little bit of the phase to tell you whether it's an inverting transfer function or a non-inverting transfer function. So most of my slides, though, are kind of showing finding the phase method. Like, okay, for high pass filter, the phase omega naught occurs at 45 degrees, right? And so then I would just look it up. But if I were to, right, all I need to do is an asymptotic Bode plot. Where is, okay. Here's the high frequency gain. That's one asymptote. And let me just try to draw that straight out. Then here's the other asymptote when it's really just something divided by S. Okay. And where they intersect, and you can see I'm kind of drawing it so I'm getting the same thing. All right. But if you were to draw the magnitude exactly these two asymptotes, it would line up in the same spot. The only difference here is the it's really a hand extraction, right? An intuitive extraction. So omega naught is 2 pi times a kilohertz. Great. It's a high pass filter. Good. The gain at high frequencies is 0 dB or 1, right? And well, that's it. Okay, that's a first order filter, right? And yeah, you could call this FC. Sometimes you call it F naught, right? And I don't know. It's also can be called the bandwidth. The bandwidth of the filter is, the high pass filter is like a kilohertz, right? You'd say, all right, that's the cutoff frequency. Although it's used more with the low pass. Okay. So here we have, 2 more examples where we have a high pass on the left and a low pass on the right. I have, it's still first order because it's going from 90 to 0, and this is going from 0 to minus 90. Right, so that's one indication that it's first order. If I went and checked the slopes, you'd see that it was positive 20 dB per decade, minus 20 dB per decade for the low pass. Right, now before the AC gain was 1, right, for both cases, or it was 0 dB. Well, now it's 40 dB for the high pass case and 20 dB for the low pass case. So you just have to convert that into a linear term, okay? And then you just, write out what is a first order low pass transfer function, S divided by S plus something, right? The something is omega naught, right? But then everything is multiplied by the gain, 100, right? Now, when we look at the low pass filter, right? Again, we're getting omega naught again at 10 kilohertz. So omega naught is 2 pi 10 kilohertz. The DC gain is 20 dB or 10, right? And then you have to remember that for the low pass, right, it's omega naught S plus omega naught times the gain. Where here, it's S plus omega naught times whatever the gain is. All right. Let's just, so again, I can come off of the 45 and find it. For this case, I can come off of the minus 45, right? And then if we choose to do the asymptotic plot, right? There's a high frequency asymptote. Here's coming up from low frequency. Okay. And right there, it's the same position. Same thing. Low frequency asymptote, high frequency asymptote. And again, I'm kind of sloppily drawing. Drawing it, okay? But that's how I can find omega naught as well, right? And what I found, like using measured data, this method seems to be a little more reliable, because trying to get the phase is really hard to calibrate, because it's dependent on the length of your probe tips and the velocity that the signal is traveling through your wires. But you can certainly tell if it's inverting or not inverting. Okay. So Nick, cutting, do you see, does that answer your question about calculating the cutoff frequency using the magnitude of the transfer function?
Yeah,
high and low
that's
pass?
perfect. Thank you.
Okay, yeah. And so actually I want to make sure I get the name right. Okay, so now Eric, here, this is actually going to be your answering your question. All right. So it's a low pass filter because it starts, the gain is high, and then as frequency increases, it decreases, right? I can actually see two distinct breakpoints, right? And that's like midterm 1, where you would plot two distinct breakpoints, because I only ever gave you real poles, and the poles were separated by a decent amount so that you could definitely see two different breakpoints. All right. Now, the thing is the cutoff frequency of the filter actually would be called this, or the bandwidth. And it's really at this point, which is kind of the minus 3 dB point. And that is just, you could call it an industry standard, right? That's the definition. And so somewhere in here is a minus 3 dB point, and that would be the cutoff frequency. But notice omega naught is actually here. Well, in a high pass, it'd be the second. Let's get to, it's great that you're trying to abstract it, okay? But maybe hold off on abstracting it just yet, okay? But now, so omega naught is, unless it's really underdamped, isn't, well, anyway, you'll just see. So now it's second order, right? Omega naught is going to occur at minus 90 degrees, right? So you come out here and bring it down, and it's, what did I change it? And now, and in this example, it's 100 hertz. Okay. Now, this is the interesting part. This still works with the magnitude, but you just need the extreme asymptotes. So, oops. So I'm going to try to draw this extreme, right? I'm drawing that extreme out. And then this one, I'm drawing this extreme out. Now, yeah, there's another asymptote in between, right? That, yeah, could be used to get your 2 points, but really, that could be your F naught, which then turns into your omega naught. And the larger the damping ratio, right, the more overdamped you are, the more these 2 points spread away from the center. Okay. So again, by the shape, we see that it's low pass. The phase goes minus 180 degrees. That's indicating that it's second order, right? Seeing 2 poles like that is indicating that it's second order as well, right? Again, to find the DC gain, set J omega equal to 0. This goes to 0, this goes to 0, the omega naughts cancel out, and you're left with GDC. All right, and you probably have 40 dB memorized as 100, right? So that's that. The omega naught squared, right? We found that, and it's left to find the damping ratio, right? So now we get to use some imaginary number things. So for the high, for this region, we let J omega go to 0, right? But now we want this point here, and it's a good point to check for low and high pass filters, because if I set S equal to J omega, it's not 0, it's not infinity, sorry, it's J omega. Well, when you start substituting that, doing the complex algebra, what you get is whatever the DC gain was, we've already measured that, at minus, and this happens at minus 90 degrees, which is where that minus 90 degrees was coming from all along, right? And so you just read the magnitude at that point, which looks like it's 15. No, I said it was 14. That's over here. So I read this off the chart, right? 14 dB. Convert that, it's 5. Then solve for the damping rate coefficient, and it's 10. It was 10, I know, in the example. But again, doing it with values that you can read off of, just, without extracting it with LT Spice, that's pretty good. All right. And so again, recognizing low pass, that the phase goes to minus 180, and you can take it in between, or you can find omega naught with these asymptotes. Okay. But knowing that it's a low pass, and then making sure that, okay, that the omega naught is here in the numerator. The gain DC, of course, is in the numerator. But notice the polynomial is the same. Okay. This is the derivation of where it comes from. So Eric, your question about the omega naught notation, was that answered?
Yeah, somewhat. I'm struggling to understand where you got the -3 decibels and the 2 to the 1/2. Could you clarify that, please?
Okay. So before we move on, yes, Sam, gain DC is given from the Bode plot, right? You let J omega go to 0 or very close to it, right? Well, 100 millihertz is very close to 0. So the gain is 40 dB, right? Convert that into linear and it's 100. So where does this come from? It's easier to go to the low pass filter, right? So what is the magnitude when S equals J omega naught, right? Well, we substitute J omega naught, right? The omega naught is cancels out. And so we have the gain DC, J plus 1, convert that into polar coordinates, and we get 1 over the square root of 2, which is not what I said over there. Okay. But basically the magnitude of a first order system. So that's approximately -3 dB. It's not exactly. All right. But yeah,
I see.
that was a typo.
Okay, that was good. Thank you.
Was that the question? Now I can't see the question, but okay. I know that. All right. Okay. Now the thing is in our asymptotic Bode plots, I'm just gonna, right? We only ever did this, right? And we draw it like that. But really, you know, it's doing something like this. And that point was -3 dB down. We just didn't use it much because we were drawing the asymptotic plots. Okay. Now, so far we did a second order underdamped, overdamped, which gave us 2 real poles. And so that was still midterm 1, right? But now we're going to have complex poles, right? And the damping ratio is going to be less than 1. So again, we recognize low pass filter. We see, and it might be a little bit hard to see on your screen, but the phase is going from 0 to -180. Now in here, this region near the peak is certainly not, you know, -40 dB per decade, but out here it is, right? So again, we can just go from -90 over, read off 100 hertz. But you can still do the asymptotic Bode plot, but just from the extremes. You would draw this out and you would line it up here. Okay, it's hard for me to draw, but it should line up in the same spot. Okay. Graphically, it doesn't look so. Well, so again, what makes it second order, right? You know, you want to do it intuitively, let's say. right? Well, the phase 0 minus 180, that's something that's, pretty straightforward to read. This peaking is definitely a second order type phenomenon. Second, it's a complex pole phenomenon, right? Complex poles come in systems that are second or higher, right? And the phase is changing very rapidly. Notice that, from here to here, right, there's a phase change. But in this one, the phase change is so spread out that it almost flattens out, right? So that's where you can see that it's a second order, right? Now again, the DC gain is the same, right? It's low frequencies. Minus 40 dB leads to 100, right? Omega naught, however you calculate it, was still 2 pi 100 because I'm doing the same example, right? Now, we set S equal to J omega naught. And when we do that, yeah, we get our same thing, gain DC divided by 2 damping ratio at a phase of minus 90, right? So I read this point off, 60 dB. Now, if I said 59.99, then I was using the cursor, right? I convert that and I'm getting, 100 divided by 2 damping ratio, solve for that, and I get 0.05, which is certainly less than 1, right? Our Butterworth second order anyway was 0.707. Okay. So we have omega naught, same way, gain DC, and then zeta. And then, of course, fitting it into the correct equation. Now, what I skipped was this one, where the poles are repeated. All right. So hopefully you can see asymptote gives me omega naught, gives me the frequency. Now here's the thing, what's this spot here? And it's kind of, people always assume that this is minus 3 dB, and it's not, right? In this case, when we measure that spot, it's 33.94, effectively 34 dB, right? So if we were at 40 and we went down to 34, that's minus 6 dB. And so this spot in a second order system does not have to be minus 3 dB. In fact, here it's higher, it's greater. Okay. Yeah, I did it out of order and I apologize. So omega naughts, we calculate that the same way or extract it however you want. What's different is that H at omega naught is now 34. And the other example, it was 59.9. And in the previous example, it was 14. So given that all of these have the same phase change and the same omega naught, what we're seeing is the magnitude of the transfer function at omega naught getting bigger the smaller the damping ratio is. So, because it's an easy spot. Why do we use this spot is because the math works out. And so that if I put j omega naught, right, s squared becomes minus omega naught squared. This becomes 2 times the damping j omega naught squared. And then this becomes plus omega naught squared. These two cancel each other out. And then this omega naught squared and that omega naught squared, they cancel out. And so now you have something that does, if you're at omega naught squared, it drops out of your equation, and you can get this very easy gain DC divided by 2 damping ratio at minus 90, but you don't have to really do any complex math because, well, you extracted it at minus 90. So that's really what's going on, right? Did that answer your question, Nick? Oh, okay, good to know. Okay. So we've been kind of, we did low and high pass first order, and then we did over critically and under damped for the low pass. I did want to make sure I don't run out of time and talk about the notch filter, which is, and the band pass, which are trickier. All right. But here's the thing, the high pass, you know, really what changes? Well, the denominator is still the same, right? But now the numerator is different. So Rudy, your question about looking at for first order when the phase is minus 45 and for second, it's minus 90 degrees for second order. Yes, that's where you're picking up omega naught. But for a high pass filter, it's plus 45 and plus 90 and plus 180. No. Omega naught is at plus 45 and plus 90 for high pass. All right. But again, you can still do this with the magnitude technique, right? So now phase is 180 down to 0. So that's, you know, second order and telling you that it's, you know, a high pass. But I can see 2 breaks. So whatever zeta is got to be greater than 1 just for looking at it, right? So you can pull it off for plus 90, right? Or again, these asymptotes, right? You can pull it off either way. Okay. Let me make, okay, yeah, here's where I did, this is where I did the work, right? But when S goes to infinity, right, that's where we get the high frequency gain. In this case, it's 14 dB or a linear of 5. Omega naught is 2 pi times 1 hertz. So I changed that, right? And then I extracted the magnitude here at omega naught, solved, and I got 15. All right. So then this is the complete answer. And actually, in your exams, you can write it like that. 2, here's the damping coefficient, and then 2 pi, whatever, things are, right? For here, you can write 2 pi, whatever the frequency is, and then just square it. I can really see what's going on, and it's less chance for anyone to make a mistake with their calculator, okay? Now here, it's underdamped, but this peak, just so you know, is not omega naught. It gets closer and closer the more underdamped you are, right? But here's my high frequency gain, right? I'm measuring 10.175 micro dB. Well, that's effectively 0, right? I find omega naught, however, which way works, and I measure that spot right there, which is 34.5 millidB, right? So again, the AC gain is 1 minus 34. It's almost 0, right? But still, and so I get a damping coefficient of close to a half. All right. Now, for the bandpass, it's not as straightforward. All right. Although I have a feeling. So the phase goes from plus 90 down to minus 90. And so you actually take the phase halfway through that at 0. And then that gives you omega naught, right? Or you can really look at these, kind of drawing these two asymptotes, right? And so, it's the middle, right? Because it's symmetric. The cutoff frequency is in the middle. But what happens is, that's pretty straightforward to get, right? And then you're thinking, well, let me substitute j omega and I'll be able to calculate my midband gain. But the midband gain isn't this spot here necessarily, right? And so really the midband gain, you don't really know, right? And you don't know the damping coefficient, right? If you look over here, S times omega naught midband gain. So yeah, you know omega naught. Oh wait. But you don't really know these two things. It's not like the AC gain or the DC gain where you can just read it from there. So you end up having to come way out here when S is either a lot less than omega naught or S is a lot bigger than omega naught. And what happens is that if either of those cases happens and you work through the math, that at minus 90 out here, or no, when S is much, much greater than omega naught, you're at minus 90, right? It's just you take whatever the magnitude is at that spot and set it equal to omega naught divided by that. And so you get gain midband 10. And then you can come back here and calculate your damping coefficient. All right. So it's a little bit trickier. Why out here is that because if S is so much smaller than omega naught, right, it stops becoming complex, right, in the denominator, and S times here is just whatever frequency you're at, in this case 100 hertz, right? And it tells you to so this is your 100 hertz, this is your omega naught, and that's your gain at that spot, and you get 10. Or conversely, out here at minus 90, your frequency is that you're extracting at is 2 times pi. You're extracting out here to that gain divided by S, and you get 10. All right. So it's a little more involved. And you can see that the more the damping ratio, the smaller the width of this kind of area gets smaller as well. All right, and these are just examples that you can follow. All right, so it's pretty wide. Now this is repeated poles for the zeta is 1, right? And then if we have complex poles, you can actually start to see a peak. All right, that's why that midband gain isn't really that spot. All right, so there's 3 case studies there. Now the notch filter. How to put it? With the low and the high, it was very easy to find everything you needed. But with the notch, omega naught is still easy to find because it's right here at the notch frequency, in this case, 10 kilohertz, right? The AC gain is easy because it's just, you pull it right off of here. And the DC gain is easy. But the complex math there's no easy way to solve for this. And if you look at one of my old solutions, it kind of goes on for pages. However, so omega naught is still found just by looking at the middle, if you will. So if you take a bandpass and invert it, right, it's right in the middle. That's easy, right? It starts at 0, goes down to minus 90, up to 90. There's your 180 degrees change in phase, right? But it starts and ends at 0. That's easy. The AC and the DC bit is the same. But the way you do it is to find the damping coefficient is that this is the regular equation. However, there's something called the stop band width. And in fact, that's equal to 2 zeta omega naught. So if I replace 2 times the damping ratio times omega naught with the width of that region, I get the same thing. And that width of that region is from minus 3 dB point to minus 3 dB point. So in this example, the AC and DC gains are 20 dB, right? Omega naught is 2 pi 10 times 10 kilohertz. Straightforward. Now what I need to do is measure this width. That was bugging me. So since we're at 20, what's that minus 3 dB point? You'd say, well, it's 17 here, 17 here. And when you do that, the width of the frequency region is 14.28 kilohertz, right? Well, when you solve for the ideality, the damping ratio, you get 0.714. Well, I set this up to be a Butterworth notch filter. And so it should have been 0.707. Well, why didn't I get exactly the right answer? I mean, I'm pulling it right off of LT Spice. Well, that's because the minus 3 dB point isn't really the minus 3 dB point. So if I take 20 dB minus this ratio in log, it's 16.989 dB. So if I measure from 16.980 to 16.980, then actually I'll get 0.707. But really, that's there is no way you're doing that by eye, right? And so, but what can see is that the wider this is, right, the larger the damping ratio will be, right? So there's 2 notch filters in the homework. Really, just do it this way. You find omega naught because it's the right where the phase changes, right? And the magnitude is the minimum. Just like, right in the bandpass where the magnitude is the maximum, right? But you can just measure the width and come up with omega naught, with the damping ratio. And then the AC and the low AC gain. And what I suspect is that if I measure, what I don't know is, can I get away with this minus 3 dB point here to get the width? And it works for the band pass too. I haven't tried it yet, but that might even make the band pass filter even easier, where it's just the width. Now, yeah, can you say what's the width here? Hard to say, because would I go from a certain phase to a certain phase? You could say that's a thing for research. All right, meaning I don't know. So okay, so actually that's a great segue question, Vicente. Let's look at what happens to zeta. So this is a high pass filter, low pass filter, right? And omega naught is all the same. It's 2 pi 100 kilohertz. And notice the phase is all crossing at minus 90, all at the same spot. So this is one of my LT Spice simulations where I just vary one thing, right? And this blue here is 0.1, right? And then 10 would be this flat point here. Okay. And so that's now, how is it that I know that one, I mean, the truth of it, right, is 1 is critically damped, greater than 1 is over, under than 1 is underdamped. Well, I've been doing it for so long, I've memorized it, right? So that's really how I know, but I don't think that was your question. Okay. Um, but it's a good question. All right. So let's use the quadratic equation. B equals 2 damping ratio omega naught, and C equals omega naught squared. All right. So over, under, and critically damped is all about what's in here, right? You know, what is equal to what, right? So two. So let's take zeta equal to 1, right? That's going to be 4 omega naught squared. It's going to be equal. So that's going to be 2 repeated roots. Now, if zeta is less than 1, well, we still have 4 omega naught squared zeta squared, but zeta less than 1, right, makes this less than 4 omega naught squared, right? And if zeta is greater than 1, for omega naught squared zeta squared is only going to make that greater, right? And so this format, right, it's generic. It doesn't matter what kind of filter, RLC, spring mass damper, or if you're describing a pendulum, you know, a swinging ball, right? It's all the same. And that damping ratio tells you whether you have complex poles or not. And yeah, okay. But it's the same way. How do you know what things are? If it's S plus R over L, S plus 1 over LC, it's the same thing for series connected RLC. And for a parallel connected RLC, right, we have that. All right. So that's, now I'm not criticizing. I'm trying to tell you, should have seen this somewhere in differential equations a little bit if you're trying to relate old knowledge to new knowledge. I'm not saying your differential course was bad or, you know, you should have remembered it. I'm trying to help remind you where you might have seen it the first time. Okay. Now, Vicente. Oh, Sam is telling me it's 4:14. I think that's probably it for today. I know you have differential equations. As a reminder, we don't have class next Wednesday, but you know, that doesn't mean we don't have class on Monday. You know, let's try to Let's try to make it to class or listen to the lectures. And, you know, let's, I never thought I'd hear myself say it, but, you know, let's be safe this Thanksgiving. Okay. All right. Have a good day, everybody.
Thank you.
Oh.
Have a great weekend.
So the final exam is everything's the same. Although I am interested in your opinion on whether for the future, I should use like a lockdown browser or Proctorio. You know, if you have an opinion about the way that it's run with like multiple questions and multiple answers and versus everybody gets the same exam, but we use Proctorio, right? You know, let me know. But really, mom will deliver the exam, but it'll be hand graded. Okay. Yep, I know. I guess, but I mean, not today. You can send me an email, okay? Harsarup, okay? That's why I do it this way. But stress free. I was freaking out, Karan. Oh, and harder with a Mac. Okay. All right. Anyway, it is a lot of effort, I think, on your part and my part to do it this way. So if you like it this way, again, send me an email. I know you guys got to go. This wasn't an official survey or anything like that. Okay. Yes, Prehan, it's the final exam is 10 questions and you get, you know, final exam time. And AEC accommodations are scaled the same way. Oh, and remember, if you have more than one exam, if you have 3 exams within a 24-hour period, now is the time to start figuring that out and asking professors. Okay, take care, everybody.